Okay, good morning, everybody, and welcome to February 10th, 2022 WESTalks. As always, WESTalks is hosted collaboratively by IC Impacts and UBC Future Waters, and also the University of Victoria. And here's your organizing committee: Abhishek, Lily, Fuhar, Jaskran, Kelsey, and myself. And Furia helps us with the admin stuff from WESTalks, or from IC Impacts. Here's the global map, like we always like to share, and I'll post the link to this in the chat in a second. But if you haven't done so in the past, please add yourself. It's very cool to see all the diverse backgrounds and cultures of people that we have participating and sharing in WESTalks. All right, here is the speaker lineup for winter and spring of 2022. We started with Dr. Preston Mansfield back in early January, and we have talks all the way up until the West Conference, which is scheduled for June 8th, 9th, and 10th. More details on that, hopefully by the end of this week, maybe early next week, we'll share with the WESTalks community. But today we have Dr. Jessica Ray from the University of Washington, who's going to tell us about stormwater management and treatment. As always, the previous WESTalks are available on our YouTube channel. If you just search IC Impacts and like WESTalks in the little search bar on YouTube, you'll be able to find those. All right, and so it's my pleasure today to introduce our speaker, Dr. Jessica Ray. She's the Robert and Irene Sylvester Assistant Professor in the Department of Civil and Environmental Engineering at the University of Washington. Ray received her bachelor's in chemical engineering from Washington University in St. Louis. And then after graduation, she stayed at Washington University in St. Louis to get a master's and a PhD in energy, environmental, and chemical engineering. During her PhD, Ray employed surface chemistry techniques to investigate interfacial reactions of nanomaterials in water. She then moved to California as a Miller Institute postdoctoral research fellow at the University of California, Berkeley, in the Department of Civil and Environmental Engineering. And there, she developed low-cost polymer clay composites to treat urban stormwater. And I think it's the first talk we've had in WESTalks about stormwater. I can't believe it's taken us this long to incorporate this, but that's very exciting. Now at the University of Washington, Dr. Ray is continuing to develop and characterize new composite materials for selective contaminant removals in water, for enhanced degradation of persistent contaminants, and for the recovery of valuable species in waste streams. And in recognition of her novel interdisciplinary research addressing urban water supply and sustainability, the Chemical and Engineering News named Ray one of the talented 12 honorees for 2020. All right, so I will stop sharing and we'll get on to the important talk of the day. Dr. Ray, please take it away. And for anybody in the audience, please post your questions in the chat box throughout, and Kelsey's going to get to those at the end.
Okay, great. Thanks so much for that introduction. Can you see my screen? Everything's okay? Okay, perfect. So yeah, thank you very much for the introduction. Happy to be a part of this series. So today, as mentioned, I'll be talking about urban stormwater management and treatment, which is, depending on where you live, something you either don't think about a lot or something you think about quite often. So this was work that I was doing at UC Berkeley, and I'm now continuing this work at University of Washington. Okay, so I'll start with just a bit of a framework here about the natural kind of water cycle and what most people think of when they imagine stormwater. And it's this kind of pristine image on the upper left here, where rainfall is occurring over large open forested landscapes, and you have this nice kind of recharge of groundwater that then goes on to participate in the water cycle. But what we know from just looking at trends over the last tens of years is that a lot of us, the global citizens of the world, are living in more urbanized areas. So instead of this nice open forested landscape, most of us are living in cities like Seattle, Washington, or in Vancouver, and we when it rains, we, instead of this pristine image on the upper right here, we have more stormwater runoff blowing over engineered surfaces. And this is important to consider how this is impacting the kind of natural hydrologic cycle because of this rapid population increase and urbanization across the globe. In fact, the United Nations predicts that 68% of the world population is projected to live in urbanized areas by the year 2050. So if you think about, again, this comparison or juxtaposition, that's going to be a huge shift going forward. And so living in Seattle has been very great in terms of the work that we do around stormwater management and treatment, because King County, which is the largest county in Seattle, Washington, has done a lot of public awareness around the kind of complications of stormwater. So here's some nice figures that I pulled from their website, and I'll direct you to this kind of schematic on the right that gives you a bit of an idea of the volumes that we're talking about in Seattle with stormwater. So if you have an acre of open forested land cover in King County in Seattle, that will equate to about 800,000 gallons of water that either replenishes nearby groundwater and aquifers or is evaporated. And in comparison, if you are in, say, downtown Seattle, in very urbanized landscapes with lots of buildings and roadways, then you have the reverse effect. So you have over 800,000 gallons of now polluted runoff entering the Puget Sound. So again, if you think about, especially in places that heavily rely on their groundwater supply for drinking water or for agriculture, you have this, again, significant shift in the amount of rainwater that is going to recharge those groundwater aquifer stores, now flowing over streets and then being discharged to a nearby body of water. And in fact, again, this is information from the King County website, about 1/3 of pollution in Washington state, of water pollution in Washington state is attributed to stormwater runoff. And that's impacting over 50% of all salmon and steelhead runs in the Puget Sound. Okay, so when we, again, kind of zoom out and think about how we typically manage stormwater in the US and in other spaces as well. So when you mismanage stormwater, you have situations like this where you have flooding over streets, and if it's a lot of rain, you could even have backup into buildings. And so the traditional approach is just to get the stormwater off of the street as fast as possible. So a lot of the storm drains are installed to kind of combat the increasing volume of stormwater runoff flowing over streets. But instead, we could think about better ways to manage stormwater. So instead of just installing a lot of storm drains and then conveying that water to that stormwater into a nearby body of water, we can install these relatively low impact systems that can help manage the stormwater. So from left to right here, we have a rain garden. You've probably seen a lot of these in parking lots, also shown here on the right, where stormwater is conveyed from the street to kind of participate in local groundwater recharge at this site. And you could also have pervious pavement or permeable pavement, where you, in spaces where you would otherwise have completely paved over land, you could leave these kind of open pockets where rainwater can naturally participate in the hydrologic cycle. And if you are afforded the luxury of more space, you can build these kinds of detention ponds where you are capturing the storm water and then conveying it to essentially a man-made reservoir where that water could be treated or could be used as a backup water supply. And this is particularly important considering that over, I believe, 35%, at least in the US, population lives in coastal areas. So a lot of those coastal areas have a myriad of complications with respect to nearby water supplies that they have available to them. And in places like California, where I was doing my postdoc work, there's a lot of focus on the potential of stormwater just to augment the urban water supply and serve as a backup reservoir in cases of extreme droughts, which is kind of suggested here. And then just around our neighborhoods and businesses, we can also think about better ways to manage stormwater. So here's an image that I captured when I was out walking my dog. There's a bunch of these in buildings and homes around the Seattle area, and King County and Seattle Public Utilities has this RainWise program that incentivizes businesses and homes to practice stormwater management or better stormwater management systems at home. So you could collect that stormwater from your roof and then use it to water your lawns, if you have a lawn in front of your house or in the back of your house. And on a larger kind of citywide scale, you could use it to irrigate parks as well. And this is, something that it's not commonly done, but if you think about the water that is used to irrigate your home lawns and lawns and or parks, it's drinking water quality that we're using to do this. So obviously we don't need drinking water quality to just water your grass, and instead we could use other water supplies like stormwater. And I've been hinting at this, but the complication with imagining new approaches to how we use stormwater or better manage it is that it is often very polluted. And again, this connects back to the fact that we're living in very urbanized areas and densely populated areas with lots of engineered surfaces, as shown in these two images here. So if you think about a typical suburb or kind of downtown urban space and rain falling over these spaces, there are unfortunately tons of sources that of contaminants that will leach into the stormwater, and then that contaminated stormwater will then be conveyed to a nearby body of water, where it could then go on to have negative environmental and ecological impacts. So here are just some examples of where contaminants appear from these engineered surfaces and these different landscapes, and how those contaminants are being conveyed in stormwater. So on the kind of suburb side, we have a lot of excess nutrients from lawns and fertilizers that have been applied, as well as herbicides, insecticides, and pesticides. If you, again, think about not only suburbs, but also just agricultural landscapes where there's a lot of excess nutrients and chemicals applied. Animal waste, again, as a dog owner, I notice a lot more animal waste on sidewalks and grass than I have ever in my life. So that could also, contaminants in the animal waste could be washed away by the stormwater. And in addition to actual litter and waste, road dust, flame retardants and auto exhaust, both, in the stormwater, but also, of course, in the atmosphere as well. And then tires, which are an emerging source of contamination into urban stormwater. In fact, a colleague in my department, Ed Kaloje, in the Civil and Environmental Engineering, has published a study in Science recently that highlighted this issue of a tire rubber constituent that was leaching into stormwater runoff, and that stormwater runoff was being conveyed to a nearby creek where salmon were spawning, and they noticed a very high mortality of coho salmon in particular that were dying after receiving the stormwater, after the creek received stormwater from this nearby highway. And let's see, I tried this before. I'd like to play a video of, hopefully you can still see my screen. Can you hear this? Okay.
We're here at Longfellow Creek in West Seattle, and this is one of the first places where 20 years ago we were documenting how many fish were dying when they came back to spawn. We have this chemical soup that washes into these creeks in the fall when it rains, and we know that there are thousands of chemicals in that soup. So what chemicals are killing the coho? Is it 100 chemicals acting all together to kill the fish? Or could it be one or two chemicals that are just really toxic?
My name's Ed Kaloje, and I pretty much work at the intersection of water, chemicals, and fish. When it rained, we saw a whole bunch of chemicals from the roads in the creeks. So we started collecting water samples and trying to figure out what chemicals were in these creeks when the salmon died. We pretty much figured out that anywhere there's a road and people are driving their car, little bits of tire end up coming off your tire and ending up in the stormwater that flows off that road and even into the urban creek.
When we discovered that it looked like tire wear particles were the source of these chemicals, what we did is we made a whole bunch of tire particles, and then we passed water over those particles as if it was raining and water was flowing over them. And now what happens is that you get chemicals actually dissolving from the tire particle into the water, and it killed the fish.
And that's the time that our group is coming in, because we are really good at chemistry. We are the environmental chemist, and we figure out the chemical in there and turn out to be a totally unknown chemical.
The chemical that seems to be really problematic and toxic to these fish is actually a preservative for tires.
And to finally be able to identify the cause of that mortality is really groundbreaking. To be able to get to the point where you're identifying a single chemical, and especially a new chemical that nobody had previously known was there, is very unusual.
I hope we can get to a point where we have salmon-safe tires. Tires that are safe for not just humans driving on them, but also the fish and the organisms that are exposed to roadway runoff. I think that's important.
Okay, so again, like really interesting work that was done by my colleague, and now it's, unfortunately, it's studies like these that are, or I guess fortunately, it's studies like these that are really raising public awareness about the negative impacts associated with urban stormwater runoff, and especially considering, again, increasing urbanization and population, so more introduction of anthropogenic chemicals into our daily practices that might end up in stormwater runoff and then could lead to very severe environmental impacts. Okay, so let's return to this rain garden scenario as a typical stormwater best management practice. What we did analysis in 2020 identifying different stormwater best management practices, BMPs, and we looked at this international stormwater management database and looked at the number of sites that were reporting data and looked at a couple of representative contaminants. So lead, zinc, total nitrogen, total phosphorus for nutrients, for example. And here we have different types of BMPs. And what we're looking at here is, again, how many sites are reporting data, and then the removal efficiency for each class of contaminant that we selected reported from the data. And so the takeaways from this figure in the study that we published in 2020 are that there are only a few sites reporting any data. So if you think about your average, kind of rain garden or like permeable pavement, some other stormwater best management practice, these sites aren't collecting any data. So we don't know what contaminants are going into these systems and the efficacy at which they're removed by these systems. And according to this figure on the bottom here, we have low or variable removal efficiency for these different types of contaminants. And what's also important to note is that, the site only reports maybe, 50 or so contaminants, but there are literally hundreds to thousands of compounds and chemicals that enter, stormwater runoff that are not being tracked at all. So what my group is interested in is looking at existing stormwater management practices like this bioretention pond, and understanding these kind of natural processes that are occurring where we have rainfall over engineered landscapes that convey stormwater contaminants into these systems. And recognizing that these systems typically contain, soils, gravel, sand, compost in some locations. And you can get some natural attenuation of contaminants and stormwater runoff in these systems, but clearly from the data, it's not enough. So what my group is doing is looking at development of engineered materials that are environmentally benign, but impart some reactivity to interact with these contaminants and enhance removal within these best management practices. So we are thinking about not only, of course, the design and characterization of these materials and, what types of contaminants can be removed, but also where to apply them. So we are, have embarked on this journey of investigating different types of either combinations of materials or, again, unique amendments, such as in pervious pavements or, more kind of active treatment in large scale columns, and then really understanding the complexity of these rain gardens by doing some mesocosm studies in the lab that closely mimic a rain garden situation. And so we hope to pilot these technologies around campus and in the Seattle area. So I'll give you some highlights of 2 materials that our group is working on to address this issue. So here's an image from our lab where we have this large tank here that we've created synthetic stormwater runoff when we spike in a bunch of contaminants. And then we build these lab scale columns that are packed with different either conventional stormwater media like sand or gravel, and then our engineered materials so that we can test their efficacy. So one material that we're investigating is a ferrate iron oxide, shown here, the synthesized form in the lab. And we're interested in this ferrate iron oxide for a couple of reasons. It has very high reactivity. So it can undergo reduction. So ferrate has an iron 6 oxidation state. It can undergo reduction to form iron 3 species. And just to give you some perspective here about these oxidation potentials, here we have a table showing common disinfectants used to degrade chemicals during water treatment and their corresponding oxidation potentials. So here I highlighted some typical suspects. Chlorine, ozone, hydrogen peroxide are very commonly used in water treatment to degrade chemicals. And the higher the oxidation state potential, the greater are the strength of the reactivity. And ferrate at the bottom here happens to have the highest oxidation potential of all of these different types of disinfectants. And this is really interesting because, it has this high oxidation potential, but also iron and iron oxides are a very environmentally benign species. Iron oxides participate in a lot of natural geochemical processes. They form from rock weathering. They're already used in water treatment, and their products are just, more iron oxide phases. So we have benign source material and benign kind of reaction products. But unfortunately, ferrate is pretty unstable in water. So it's got a pH dependent reactivity, and you need alkaline pH in order to maintain high reactivity of ferrate. Otherwise, once it gets introduced to water, it degrades very, very quickly. So there are some studies looking at the potential of ferrate, recognizing its potential as a benign oxidant to use. And they were trying to think about ways to stabilize its reactivity. And what was interesting is a lot of studies were identifying that the presence of silica was found to stabilize the ferrate reactivity. So in this study, which was done in air, they exposed ferrate to a silica coating and found, reactivity on the order of weeks as opposed to, days for their kind of unmodified or uncoated silica ferrate reactivity. Some other studies, again, popping up, suggesting that the presence of a silica-supported ferrate was really beneficial to enhance and prolong its reactivity. So here, this study is showing the addition of silica gel to a ferrate in solution resulted in very high, basically 100% transformation of caffeine, which is a nice wastewater and stormwater indicator compound. So what my group is doing in recognizing that, to use ferrate, it might not be the best approach to just add silica gels into a stormwater system. What we're doing instead is building a ferrate coated sand composite material. So the purple here represents the ferrate, and then it's coated on this grain of sand. The sand serves 2 purposes. It's a structural support for the ferrate coating, and sand is primarily made of silica. So the silica will then also serve to help stabilize the reactivity of the ferrate coating. So the idea is if you react this material with some representative stormwater runoff organic compound like diuron, this herbicide, it will help facilitate oxidation of the contaminant into a form that's more biodegradable than the parent compound. And then Once this reaction occurs, the ferrate will be reduced to iron 3 species. And then the iron 3 species is very well documented to help absorb trace heavy metals as well. So we get essentially dual treatment of trace organics and heavy metals by one engineered reactive material that's also environmentally benign. So we are investigating the leaching of the iron oxide, the reactivity, what oxidation states are present on the coating and in solution, what's happening to these contaminants as they're interacting with the media, and what happens when you have competition of contaminants for reactive sites. Here's some, a quick, how am I doing on time? I think I'm okay. Here's some quick, notes about how we make this material. We start with the sand, and we found that just, adding sand to a ferrate solution results in pretty weak binding. So what we did was we added a chemical modifier, this tetraethyl orthosilicate, to the sand surface, which, as you can see, just has a bunch of silica bonds here. And this TEOS, the tetraethyl orthosilicate, also kind of helps to create almost like a silane polymer around the sand surface. And that helps to have a greater binding affinity for when we add this, modified sand to ferrate that we're synthesizing in the lab. So we mix these two together, and then we wash and prepare the ferrate-coated sand for subsequent analyses. Okay, so some preliminary data from this material. We were interested in testing it with lead and caffeine as representative organic and inorganic contaminants in stormwater runoff. But first we were interested in, again, I mentioned that the TEOS binding was really essential for us, and this is the proof of that. So here we have time on the x-axis and then the total iron leached from the sand with and without the TEOS coating. So clearly with the TEOS coating, not only do we have more ferrate that's bound to the sand surface, but it's also stable for longer periods of time. And then we reacted this ferrate-coated sand material with caffeine and lead. Here are the experimental conditions here. And what we can see is for both of these representative stormwater runoff contaminants, we have about 75 to 80% removal of these contaminants over a long period of time. So here, probably normalized removal over time for, again, caffeine and lead. And what we are further investigating with this material is one, degradation products from this caffeine oxidation. That should be the mechanism occurring between caffeine and the ferrate-coated sand, is oxidation of the caffeine, which should then form some oxidation byproducts. We're characterizing those. And then we are also interested in any potential kind of redox chemistry associated with the lead and other heavy metals that can undergo redox changes as it interacts with the ferrate-coated sand material. So here's just, again, a snapshot of what we've been doing so far, and we're going to publish a paper soon, hopefully, about this data with these findings. Okay, one more kind of highlight of the materials that we're developing in the lab to help remove contaminants in these systems is a material called biochar, which you might have heard about before. Biochar, the bio in biochar comes from biomass. So you typically use some agricultural or food waste product to then burn at high temperatures, and it produces a charcoal material essentially. And if you take an image of an electron microscope image of this char, you can see very nice open pore-like structures inside, which are very effective for trapping contaminants in stormwater. For our particular biochar that we're making, we're using used coffee grounds, which I think is pretty fitting. Seattle's the coffee capital of the world. So we use and have a lot of food source available to us to use. In fact, we're getting ours from campus, and I believe the campus is getting their coffee grounds from Starbucks. So again, lots of source material available to us. So we were doing some preliminary testing of this coffee biochar and comparing it to a commercially available activated carbon material that is sourced from charcoal, which obviously is not the best material to use, but it's also, of course, very widely used because it is so effective at removing a lot of contaminants. And what we found was comparable performance to the commercial material for removal of perfluorooctane sulfonate, or PFOS, which is a very toxic flame retardant that I'm sure a lot of you have heard about as well. So again, we have some research questions around this material. What's its absorption capacity? What types of contaminants can be removed? What are its properties with respect to stormwater infiltration systems? And with all the materials that we're synthesizing, we're interested in these questions too, right? So how long does media last if we were to implement it into a rain garden, for example? How long will we get contaminant removal? And what are the potential downsides of doing this kind of amendment? So this work was supported by Washington Research Foundation and the University of Washington Innovation Hub, CoMotion. And we actually filed, it's actually a full patent now, I should have updated that. So we have a patent on this material, and we're doing a lot of testing with the biochar for a lot of different applications. Okay, so one of them, of course, is that stormwater treatment. So here I have an image of columns that we've built in the lab. And here we have sand-only columns, and we have increasing amounts of the coffee ground biochar. And we are feeding synthetic stormwater into these columns, each at 50 microgram per liter. And here the trace organics that we have added into the synthetic stormwater that's being treated by these columns. And the highest weight percentage that we selected was 3 weight percent. That's shown in these triplicate columns over here. And what we see is for, the bulk of the representative trace organic contaminants in the stormwater runoff, we have, tons of removal here. So 100% removal up until about 220 or so pore volumes, where we start to see some breakthrough of the contaminants in the column effluent. And depending on the chemical properties of the trace organic contaminant and their interactions with the biochar, we see varying degrees of removal here. So this is a great preliminary case study to say that, this material does work and can work for infiltration systems. And we're going to expand that analysis for the trace metals and other types of pollutants as well in stormwater. Again, the key with the stormwater media in particular is that we need it to be environmentally sustainable and friendly so that we don't add toxicity into a rain garden or other stormwater management practice that we're trying to improve. So just as a comparison, again, between the activated carbon or activated charcoal and our coffee ground biochar, what's nice is that because it mimics a commercially available material, it could be very easily kind of exchanged or implemented where activated charcoal is used. It's of course sourced more sustainably from a food waste product that's being upcycled into an adsorbent compared to using charcoal. And we're testing this now. It could be potentially safely composted, for disposal, as opposed to very energy intensive processes to either recover the activated carbon or, of course, the disposal in landfill that has other complications. Okay, last slide, I promise. So where I mentioned before that with the materials that we're developing in the lab, we're thinking, of course, about the field approaches. So pilot scale treatment of stormwater runoff. And some interested parties in the materials that we're investigating include the Port of Seattle. They have to manage their stormwater going into the port. So they're interested in a lot of novel treatment applications. In Tacoma, Washington, we have the Center for Urban Waters, and they're a center that works to pilot a lot of new water treatment technology. So they're interested in this material as well as the Department of Ecology in Washington State. They actually have a program for certification of new stormwater treatment materials. So we're going to explore that option as well. In addition to some nonprofit organizations, including the People for Progress in India, that have expressed interest in using our materials because they are, low cost, sustainably produced, and effective in terms of water treatment. And with that, here's some acknowledgements for funding sources in my research group, and hopefully there's time for questions. Thank you for your attention.